Okay, so our last talk today will be Effectivizing Analytic Concepts by Jack Lutz.
So thank you, Elvira. And I want to thank the organizers. I mean, you and the other organizers for inviting me. I wish I could be there. I think my favorite of my many fun sabbaticals was the time I spent at the Alan Turing year. I can't drink coffee with you guys at a blackboard, and I can't go like get a pint with you at the Sir Isaac Newton. But if you'll interrupt me a few times with questions, I'll feel a little more like I'm there. So please do feel free to interrupt. So we work in randomness, which is an effectivization of Lebesgue measure 0. And what I want to do today is present a general, if not crisp, framework for thinking about effectivizing analytic notions. And the framework is undoubtedly distorted by my own limited experience and knowledge. So I do invite your questions, objections, and contributions, both today and in the future. So let's start there. Let's start with what to us is the canonical effectivization of a concept for mathematical analysis, namely algorithmic randomness. So we start by choosing an analytic concept. And in this case, it's going to be Lebesgue measure 0 subsets of the Cantor space. And once we've chosen that, we also have to choose a characterization of the concept. And the characterization I'm going to choose is the one that Martin Lutz chose and is the most standard in American analysis texts, especially at the undergraduate level. Namely, a set Z of infinite binary strings has measure 0 if and only if, for every epsilon greater than 0, there's some set of strings such that the cylinders generated by those strings, and that C sub W means the set of all binary strings, set of all binary sequences that begin with the string W, that all those cylinders cover Z, and that their uniform probability measures add up to something less than or equal to epsilon. Okay, so there's a characterization. Then we discretize the characterization as needed, like salt to taste. Depends on the situation, but we discretize it somehow. And in this case, it's the epsilon we want to discretize. So we replace it with 2 to the minus k. And we instead get the characterization that for every k, there is an A, such that you have the covering and measure conditions. Okay, there I just repeated it on the next slide because it's not a big screen. And then I'm going to replace that by a slightly more convenient characterization. Instead of saying a set of strings, I'm going to say I have for each k an enumeration f sub k of that set of strings. So now I have Z covered by the union for all L of C sub f of L. And I guess you probably can't see from where you're seated, but there's a subscript on all those Fs, subscript K on all those Fs, not just the one where it really is. Okay. And then you scolemize as needed, namely when you have quantifiers in the sequence for every there exists, you reverse them by putting a function in place of the quantifier that exists. So you say you have a function f mapping n cross n to 0, 1 star, such that that's 2 to the less than omega, such that for every k and n, you do have this covering, and the cylinders that you're covering with have total probability less than or equal to 2 to the minus k. Okay. So now I'm repeating what I had before. Z contained in C has measure 0 if and only if you have this two input function f that does what we said it does. And this is where we actually do the effectivization. We impose some computability or complexity constraint on that f. And in particular, we say that Z contained in Cantor space has algorithmic measure 0 if and only if. Now we have a new concept, so we have to use a new term. Algorithmic measure 0 if and only if there's a computable f that does what we just said. Originally, Martin Luff used the term constructive for the measure 0 condition, but that's no longer used very much. Right now, I'm using algorithmic. Some people use effective. I'm going to use effective in a somewhat more general meaning, with a more general meaning in this talk. Okay, so now you have an effective notion of measure 0. Then I'll word this like annoying essay questions. Compare and contrast what you have with what you had. And the observation that Martin Luff and Solovay made in the same year, really, is that singleton sets always have classical measure 0, but they need not have algorithmic measure 0. Martin Luff, it was explicit in this context. Solovay, I'm citing his adding a random real to a model of ZFC, but they're the same idea. Okay, so we wind up with a definition that a sequence Z in Cantor space is algorithmically random or Martin Luff random if its singleton set does not have algorithmic measure 0. Okay, that's step 6. And step 7 is have fun with your friends exploring the consequences. Okay. Now, there were several choices that were made in that effectivization as we outlined it, including at least the following. First, what concept do we effectivize? And I'm going to say that's kind of beyond the scope of this talk, except that we should be looking for more concepts to effectivize. Second, which characterization of that concept do we effectivize? If you're effectivizing an analytic concept, you want it to be an important concept. And important concepts are definitionally robust. They do have multiple characterizations that are equivalent. And it turns out to matter a lot sometimes, because things that are equivalent at the classical level tend to get less and less equivalent as you effectivize them more and more. And what computability complexity constraints do we impose? That is, how effective do we make our new concept? And I'm going to use this terminology in this talk in a way that not everyone will agree with, but to me, effectiveness is a quantitative notion. I should be able to say this is more effective than that. Okay, so we have all this freedom and we have to decide how to exercise it. And to do that, we really need to answer a more fundamental question, which is why we do this at all. Okay. Or as I've often been asked by friends who are mathematicians, Jack, why in the world would you take a perfectly beautiful mathematical theory and pollute it with Turing machines? Pollute is probably about a median loaded word that people use when they ask me this. Sometimes it's more mild, sometimes it's less mild, but it's a good question. I loved classical measure theory, and why would we do such a thing? Now, the earliest answers I'm aware of even came before we quite knew how to effectivize things, starting in the early 20th century with intuitionists and allied philosophers. And that is to restrict the theory to its legitimate content, that somehow Cantor and Borel and Lebesgue led us astray, and we got way too wild with our non-constructive theories, and we needed to be reined in. And by somehow effectivizing a theory, we can bring it back to the only things that we should be doing. Probably my language is worded here because I love non-principal ultrafilters and other non-effective methods. And so I probably won't talk much more about that motivation. By the mid-20th century, people were viewing it from a purely mathematical point of view. Oh, the reason we effectivize is to create equally beautiful theories and have fun with our friends working on them. And that's I think, to many of our tastes. There are, I guess, two more motivations that have actually happened since I became aware of effectivization. One, starting in the late 20th century and continuing through today, is to analyze the structures of complexity classes and other small countable worlds. That is, and I'll talk about that later on in the talk, but if you want to understand the structure of a class like NP or exponential time, the thing you do is to make an effective version of some analytic structure and do that. And then the fourth one that is much more recent and ongoing is to prove new theorems in the classical non-effectivized theory that you started with. So there are four different motivations that you might have for doing this, and they all have an effect on how we effectivize the concepts. For example, if you philosophically think that things should be as constructive as possible, you will choose an effectivization that is fairly limited. But if you are trying to have as strong a tool as you can to analyze the structure of a complexity class, you will want to choose an effectivization, which comes down to choosing a characterization of the underlying analytic concept that gives you as much power as possible and still works inside the complexity class. Okay, so as I'm going to use terminology here, we effectivize theories at various levels. And in some ways, this is a controversial picture, but it's a picture that explains the way that I'm thinking about this. We can effective by various levels, I mean, things like are on the screen right now. We could effectivize at the analytic level, the boldface sigma 0, 1, or at the Borel level, boldface delta 0, 1. We could effectivize at the sigma 0, 1 level, which is what we do for Martin-Luft randomness, or at the delta 0, 1 level that we do for Schnorr or computable randomness. We could move up the arithmetical hierarchy. That's the ... in here, and so on. Below delta 0, 1, we can start talking about complexity constraints. And among those that have been most productive are to look at effectivizations that can be carried out in polynomial space, polynomial time, and that Q is not quantum, it's quasi-polynomial time, meaning n to the big O of log n time. That turns out to be useful. And I really am leaving out a lot of things with these dots. And at the bottom level, the most effective that has been extensively investigated is finite state effectivizations, or so-called automatic effectivizations. So this takes some explanation for non-Americans, maybe. I grew up in Kansas, and I worked most of my career in Iowa. And those are out in the big middle of the United States. I went to graduate school on the West Coast. I've spent sabbaticals on both coasts. But where I live and where I grew up are both considered flyover country by most Americans. You only spend time on the coasts, but you can look out the window and see all that farm field and stuff down below you. But Kansas and Iowa are flyover country. Okay. To a lot of the people in this room, everything that my mouse is now moving over is flyover country. You effectivize at the CE level, at the computable level, you'll jump down to the automatic level, but you're missing a lot. You're actually missing a lot by not going to Iowa or Kansas, but you're missing a lot by not looking at the complexity theory. And that's especially true because, okay, let me put it this way. It's a common myth that the fact that solving P versus NP requires, for example, non-relativizable methods, that is often summarized by complexity theorists incorrectly as meaning that diagonalization will not work. Kozin in a 1980 paper proved that any proof that P does not equal P space translates to a diagonalization proof. And something similar is probably true for P versus NP, which is $1 million problem. And a lot of you guys are a lot better at diagonalization than most of the people in complexity theory. So you're missing a lot of fun by treating this as flyover country. Okay. So let's go on. Now, I want to emphasize again. So I've said that it's important what level of effectivization you do, but it's also important which characterization you choose. And it often grows as we go down to more effective levels. An exception is actually at the finite state level. So often you'll have definitions that are equivalent classically, and then as you move down and effectivize more, they start splitting up, but some of them come back together at the finite state level. Maybe that's why it's flyover country in between, I don't know. Okay, so the rest of this talk I'm going to spend on the last two reasons that I gave for effectivizing analytic concepts. And I'm going to address them in reverse chronological order. So the first of them was to prove new classical theorems. And the second was to analyze the structure of small worlds. Okay, so to prove new classical theorems, I'll start with one classical theory. It's probably not the one you think I'm going to say. It's analytic number theory. I'll get to the other one. Okay, and specifically Borel normality. We'll work in a base B, at least 2, and hence we're working in an alphabet of the base B digits. And for S, an infinite sequence over that alphabet, and W, a non-empty finite sequence over that alphabet, and some N, we'll define the nth frequency of W and S to be that expression, which just means that you take a window of the same length as W and you slide it over S until you've slid over N symbols. And then you take the frequency with which you were looking at a W while you did that. Okay, and a sequence is defined by Borel a long time ago to be normal if every W has its fair share of the frequency, namely that frequency that we just defined. If we take its limit as n goes to infinity, that limit does exist, and it is b to the minus length w. And the really nice theorem about this, due to Schnorr and Stimm in 1972, that in some ways wasn't appreciated for a while or not noticed for a while or something, is that Borel normality is finite state randomness. The proof uses, well, the the fact uses a finite state effectivization of Ville's 1939 martingale characterization of Lebesgue measure zero sets. Namely, Schnorr defined finite state gamblers and proved that a sequence is Borel normal if and only if no finite state gambler can make unbounded money betting on it. So this is a really interesting case because what turns out is that the finite state effectivization of Lebesgue measure zero sets actually happened 60 years before we knew that it was an effectivization. And it happened a lot of years before we even knew what effectivization meant. It just happened to already be an effectivization of Lebesgue measure zero. And I guess normalities become a major topic for this community, thanks largely to Veronica and Elita, Ted, Bjorn, and others. It's cool because it allows us to use number theory and dynamical systems, Fourier analysis, uniform distribution theory, Diophantine analysis, and logic to prove new theorems about Borel normality. And it's been a major thing. What I'm going to focus on next is finite state fractal dimension. So now this is an effectivization of Hausdorff dimension at the finite state level. So it's written dim sub fs of s for a sequence S, and it's the lower asymptotic density of finite state information in S. It was first defined using finite state gamblers, a la Schnorr. And that was by Di Lathrop and Elvita Mardomo and me a long time ago. And it is definitionally robust. It has equivalent characterizations in terms of finite state compression, that was in the original paper, block entropy rates by Chris Bork, John Hitchcock, and Vinod Vinachandran, finite state log loss predictors by John Hitchcock, and automatic Kolmogorov complexity by Kozachinsky and Sasha Shen very recently. And it has a dual, the finite state strong dimension, which is a finite state effectivization of classical packing dimension. In general, those numbers are between 0 and 1, because as I said, they're densities of information. And both of them have the same, I mean, the second one is just as definitionally robust as the first one. So they're very robust notions. And a fact that was implicit in Schnorr and Stem and explicit in the Bork-Hitchcock Chandran paper is that a sequence is normal if and only if its finite state dimension is 1. That makes this the only world in which we are sure that dimension 1 and random are equivalent. All the other worlds that we work in, there are randomness implies dimension 1, but the converse is not true. But in the case of finite state randomness, it's equivalent to dimension 1. So here's a research question. I'm going to state a thesis. It's not true, but it's at least kind of true. I'll call it the normality dimension thesis. And it says this: every theorem, there's the part that might be soft, every theorem about Borel normality is the dimension 1 special case of a theorem about finite state dimension. Okay. There are a lot of theorems about Borel normality. Erdős and others proved a lot of things in the 20th century. Okay, here are at least 3 examples where we know it's true. Copeland-Erdős sequences. If I form a sequence by concatenating the binary expansions or the base B expansions of a bunch of numbers, The classical thing is, when is that normal? The dimension thing is, what's the dimension of that? And there are strong theorems to the confirming the normality dimension thesis for Copeland-Erdős sequences. Real arithmetic, it's easier to state. For example, the product of a rational and a normal number is always normal if the rational is not zero. I usually forget to say that. And it turns out also that the product of a rational number and any real number, product of a non-zero rational number and any real number, has the same upper and lower finite state dimensions as the original number. So that's an example that I can state in limited time. And then recently, we have a Veil characterization for finite state, a Veil characterization of finite state dimension, or the Veil criterion, I guess I'd call it, for finite state dimension. Generalizing Veil's criterion for random, for normality, okay, for uniform distribution, essentially. Okay. Okay, but show me more cases where that thesis is true. Show me cases where it's false. We'll understand more. Okay, the classical theory number 2, what you probably thought I was going to say first, is geometric measure theory. There, the algorithmic dimension that we write dim of x and the algorithmic strong dimension, capital dim of x, are sigma 0, 1 effectivizations of classical Hausdorff and packing dimensions, respectively. Those are actually defined for all points x in big X, where big X is any separable metric space. For example, x may be C, Rn, or cube, whatever. Here I'm going to focus on the case where x is Rn. Neil will discuss the more general setting tomorrow. And the key to what I want to talk about here is the point-to-set principle that Neil and I proved in 2017 or so. And it says this: for every set E in Euclidean space Rn, the dimension, the classical Hausdorff dimension of that set, is the minimum for all oracles A of the supremum for all points X in that set of the dimension of that point relative to A. And the classical packing dimension of E is defined similarly, but now we have the effective packing dimension. So note that the dimensions on the left are completely classical, from the classical, beautiful theory unpolluted by Turing machines. And the dimensions on the right are very non-classical. To expand a little bit, the dimension of a point X relative to A is the lim-inf, as a precision parameter R goes to infinity, of the Kolmogorov complexity of X at precision R divided by R relative to A. And by precision R, we mean that we have to get a rational point within 2 to the minus. We mean the minimum number of bits required to specify a rational point that's within 2 to the minus R of X. And by relativizing to A, we mean that the universal Turing machine that's carrying out the Kolmogorov complexity is allowed access to the oracle A. And similarly for packing dimension. Now, back when we were first looking at this, at dimension, it seemed a little bit outrageous that we were talking about the dimensions of points. I mean, a point to Euclid is that which has no part. It's a point. They're all the same. But this theory causes different points to have different dimensions. And we had first had a clue with the correspondence principle, due to John Hitchcock, that if you have a set, if you have a set of sequences that's what, a union of lightface pi 0, 1 sets, then it's classical and constructive or algorithmic dimensions are the same. But this point to set principle is a much stronger statement of the equivalence of the classical and the crazy algorithmic viewpoints. Okay, and it's called the point to set principle because it gives us a way of computing lower bounds on the dimensions of sets by reasoning from the dimensions of points. And a typical proof, oversimplified, goes like this. I want to prove that the Hausdorff dimension of a set is bigger than a third, okay? I first say, let A be an oracle. I don't really usually have to spend more time on A than that. I just have to remember to carry A along with me in the proof. I say, let A be an oracle. Then, given the context, the set, and so on, I judiciously choose a point in the set. Maybe it's somehow random relative to A, and it has some relation to some lines or curves that are in the problem. But I judiciously choose a point and prove that that individual point has dimension at least a third relative to A, and I'm done. Okay, so it lets me reason from points to sets, and it seems to be the case that humans are often better at thinking about points than about sets. Okay, and it's actually been used to prove several new theorems in geometric measure theory, including at least the following. One category of theorem is that extending theorems, fundamental theorems about fractal geometry, from analytic sets to arbitrary sets. And this isn't something that had been neglected. People worked really hard on extending the theorems that they could to arbitrary sets. You know, sometimes they get it first for Borel sets or even simpler sets, and then they'd work their way up to analytic, and then they'd stall out, or they'd get to all sets. But for these fundamental theorems on intersections, random projections, and products, we now know that they hold for arbitrary sets, and the proofs, these things are proven using the point to set principle. And improved lower bounds on the dimensions of Furstenberg sets, whatever those are. Ted proved that the Hausdorff dimensions of pi 0, 1 sets, unlike analytic sets, need not be supported by their closed subsets. And I showed that the dimensions, that a Hamel basis of the reals over the rationals can have any dimension between 0 and 1. Okay. And there are others on the horizon. But the research challenges are, first, more applications of the point to set principle. Of course, the big one is, can we use it to prove the Kakeya conjecture at dimension greater than 2? Our point to set principle arguments, in some sets, conservative over classical arguments. And by that, I mean in the same sense that, say, non-standard analysis is conservative over classical analysis by the transfer principle. If you can prove a theorem about classical analysis using non-standard analysis, then the transfer principle translates that into a proof that doesn't use non-standard analysis. Is there something like that for the point to set principle? Thomas Orpinen has proven that 2 of Neal and Don's theorems can be proven using just classical arguments. His proofs probably aren't simpler, nor does he claim that they are, but that's at least an example where, even though the proofs were first discovered using the point to set principle, they can be replaced by classical proofs. Is that always true? And of course, a bigger question is, to look for analogous phenomena for analytic concepts other than fractal dimensions. Okay, now the other reason for effectivizing analytic concepts is to understand the structure of small worlds. And I'm only going to talk about that briefly, but I do want to entice some of you to look at this. There are 4 analytic concepts that have been effectivized to work inside of complexity classes. They're bare category, Lebesgue measure, Hausdorff dimension, and packing dimension. And by that, I mean, you can talk about a measure 0 subset of a complexity class and have that have meaning without collapsing the entire complexity class itself to measure 0. Okay. So these endow certain complexity classes with internal structure of the indicated type, even though the complexity class is countable. And so a classical approach would say, oh, it just says measure 0 or dimension 0 or it's meager set. End of story. Okay. But if you want to understand the structure of complexity classes, you want to view them as bigger worlds than they really are. I guess an analogy here for thinking about it would be if when you're a logic student, early on, you find out that every theory with an infinite model has a countable model. So the theory of the reals has a countable model, or say there's a countable model of ZF. Okay. So the reals are countable inside that model. And the question is, well, what's going on here? And the answer is, well, the model isn't smart enough to know that it's countable, or even that the reals are countable, because the function that would testify to the countability of the reals isn't in the model. That same phenomenon is what's going on here. The complexity class is countable, but it's not smart enough to know that it's countable. It's not smart enough to know that it has measure 0 or that it's meager or that it has Hausdorff dimension 0. And that can give you useful information. Okay, these effectivizations actually been formulated in a very general way so that the classical analytic concepts are a special case and the easiest special case, as your classical friends may not want to hear, of the resource-bounded theory. Most importantly, these effectivizations, especially resource-bounded measure, have interacted informatively with a lot of the quantities that complexity theorists had already been working on, including polynomial time reducibilities, NP completeness, circuit size complexity, bi-immunity, complexity cores, randomized algorithms, pseudorandom generators, natural proofs, lowness, and other things that I'm forgetting to mention. But as a result, a lot of people have written a lot of papers understanding the structures of complexity classes better by using resource-bounded measure, resource-bounded category, and resource-bounded dimension, although the latter is newer. And I should also say that in complexity theory, there's sort of a set to point principle, not a point to set principle. I mean, yeah, there's that too. Neil will talk about that. But the goal of, say, proving that P is not equal to NP, I mean, okay, I'm a logician. To me, it's trying to understand the power of a single existential quantifier. But from a practical scientific point of view, the real issue is that many of the most important problems in scientific computing are known to be NP complete. And so we suspect that they don't have polynomial time algorithms. Now you regard some particular, Hamiltonian cycle or some NP-complete problem as a point in a space. It has a lot of things reducible to it. A set of things, it's called the lower span, a set of things that are reducible to it. That happens to be the set NP. The point of NP completeness is that if we could somehow, by any means, find a point, prove that that set has an element that is complicated, then it follows that Hamiltonian cycle is complicated. And a similar thing happens even if, well, you can reason about the size in exponential time, the size of the set of things reducible to a language. And if that set is big, then you can conclude things about the complexity of the things, of the complete object or weakly complete object. Okay. And to achieve this, it appears to be essential to use Ville's 1939 martingale characterization of the Lebesgue measure. If you try to use the textbook definition of the Lebesgue measure, you will get an incredibly weak measure theory that will do none of the above for you. Okay. So Ville's characterization, martingales or something equivalent, you can disguise that it's a martingale by talking about a likelihood ratio of two probability measures or something, but martingale. The martingale characterization gives a stronger measure theory than the textbook characterization. And since the goal isn't philosophical, I'm not trying to be as restrictive as possible. I'm trying to get the strongest tool that actually works in the complexity class. And so far, that seems to be the martingale characterization. And that's all I want to say. So, thank you.
Any questions or comments? Let me see. Yes.
I really liked your slide on sort of how the motivations sort of the people in the field have changed in the past century. Is this a slide you're sort of comfortable with being attributed to yourself?
I'm sorry, say the last question again. The last part.
My question was whether this observation is something you're sort of comfortable being attributed to you in a other context, or
well, I've had a lot of fun working in this, and I guess I'll clarify more. I can't hear who said what. There was a guy named Lisa Gore who wrote a paper in 1980 talking about how to do Baire category and Lebesgue measure inside the set of decidable sequences. And he is cited in my papers. At that time, it did not appear to work in complexity classes. And at that time, basically none of the complexity theoretic ideas that resource-bounded measure wound up interacting with had been developed. But Lisa Gore did have a small world, did have the idea of making category and measure work in small worlds before I did.
I meant a different slide, but I'll see later.
Okay. You want?
Oh,
He meant a different slide.
I see. I think Yeah, Neil just texted me that I misunderstood the question. Arno is just asking if he can use that slide in his talk if he cites you, and the answer is yeah.
Yeah, so you were meaning the one on the reasons for effectivization. Yeah. Okay. Thank you. Any other comments or questions? Okay, let me just quickly check whether some other. Okay, I don't see any question. So let's thank Jack again.
Thank you very much.
Thank you. So I think this is the last talk of today. But for those of us that are lucky to be here, there is a wine event, probably not much wine, I hope, because I need to work today. So please stay. It should be from 5 to 6 or something like that. Okay, and to those that are online, I hope to see you all tomorrow. Thank you for attending. Okay, bye.
Bye.